Okay. Welcome, folks. Last official slot of the day. We learned a lot today, and we're already halfway through the conference. So it was fun. I hope you enjoyed it. I know you all must be tired, but don't worry. This is going to be, let's say, more relaxing kind of a talk, not code heavy. But I do expect that you might engage a bit in conversation. So I would say a better title of this talk is Myths, Dogma, and Practice. And that's what we'll try to discuss in the coming hour. So do ask questions. Comments are welcome as well as we go along. Raise your hand or just shout it out. I don't mind. Don't wait till the end. So I do hope that we'll engage in some dialogue and we'll exchange opinions. I'm not here to share particular pearls of wisdom. I'm here to start a discussion, actually. And in general, we as a C++ community can be quite vocal sometimes when it comes to particular topics and controversial issues. And let's not forget that sometimes people try to push their opinions as facts and try to convince everyone that we should all be in the same boat. But we come at these from different angles. We each come with our baggage, our experience, our niche, our domain-specific knowledge, and the things that we've been doing and the way we've been doing them. So we expect to have some sort of mismatch in what we each bring to the table and how we see things. So extending Bjarne's metaphor of the elephant, C++ as the elephant, I like these a bit more. So we are fragmented on many such topics. And when it comes to sources of good information available, there are a bunch, like the CppCoreGuidelines or best practices around, some of them opinionated, of course, established idioms, books, conference presentations, and of course, Stack Overflow. But mixed up in all of these are bits and pieces of obsolete information, maybe, some myths flying around, some extant bad teaching materials or obsolete teaching materials, old code style guidelines from various projects that are still around and propagate some of these techniques or idioms around. And of course, onboarding new people on existing projects and existing teams, we usually tend to align with existing practice within that project, be it great or not. And sometimes we onboard on maybe old ways of doing things or unoptimal ways of approaching things. And also, let's not forget, speaking of Stack Overflow, let's not forget that we've always been beginners at some point, and we're always beginners at something new that we're learning, some new techniques, some new language, some framework, or so on. And let's have a bit of patience and try to help each other and try to put ourselves in the point of view of the other people, asking questions, and maybe use this opportunity to reevaluate some of the things that we've been taking for granted. And I don't know who saw the first series. So this would be the series 2 of the C++ Myths talk. Last year I did at a bunch of conferences a whole other series. And it all started with, during the pandemic, I got bored and I at some point, I told Jason that maybe we should do this kind of improv session where we would just rant and try out different things. And we ended up doing a very long stream. I don't recommend you watch this. It's very long. But it was fun. We tried a bunch of things. We had fun. We had lots of interactions. People were commenting there and suggesting new things. And of course, there were some occasional mean things said there. Anyway. If you want to digest, and if you haven't seen the first part, it's around recording in a bunch of versions from various conferences. And these are the topics that I covered in the first series. If any of these are of interest to you, just feel free to watch that at your own pace. By the way, all the slides are full of links to other presentations, links to articles, and reference implementations, and some Godboard links as well. So when you get the slides, feel free to click through, and don't worry, just screenshotting now. You'll get a chance to click through them if you're interested in a particular topic. So the whole idea is I want to instigate a healthy dialogue here, so do speak up. I'm here to listen to other ways of doing things. The format, if you're not familiar with the classic confirmed, busted, and because we're programmers, plausible. Okay, I have a few test myths here. C++ is inherently unsafe, and there's very little we can do about it. Actually, we've known this years before NSA or NIST, or not exactly news to our community here. Another one, it's 2023, and we should be able to leverage the power of C++ modules to restructure our code base and improve build throughput. Yeah, pretty much busted. Where are all the compilers? By the way, highly recommend, if you want to get the latest and greatest in conformance and availability in toolchains, do watch Daniela's talk tomorrow morning. Has modules in the name at 9 a.m. And there's a nice recent article by one of my colleagues. It's a case study of Office adopting header units. And there's a part 3 coming with some numbers and stats of build throughput improvements. Another test one, coroutines shipped in C++ 20. I chuckled at this tweet from Olafur. And I very much feel that I am in this camp. And even today, we had a presentation by Andreas Fertig about coroutines. I don't know, have you been in there? Yeah. For me, this one was the one that clicked, and I think I understood the most. But I've seen many versions of coroutine talks so far. This is by far the best captured representation of the situation. It's, as usual, Kevlin is an evergreen source of wisdom. Yeah, so kinda, it's plausible. We're gonna get a generators library in 23 if you can afford to be there. That just solves just a tiny little portion of what you can do with coroutines. Another pitch tomorrow. There's an interesting presentation by Hanna Dusikova. Mark your calendars. If you are interested in this kind of stuff, you're gonna see some really cool examples. I'm looking forward to that. Okay, so I think you got it how it works. Let's dig in. And one topic that is forever important to me is tooling. And a thing that I iterated last year, and I have to do it again, just because it's too important to me, is that C++ is not easily toolable. And I've always been a tool builder. I've always built SDKs, developer tools, IDEs, and so on. So I do care about this a lot. And no matter at which spectrum of these kinds of tools you're interested in, or where you find that your pain points are, it's important to really understand that C++'s problem is not lack of tooling or good tooling. The problem is that we have too many tools. And we kind of have to mix and match. We have to spend a bit of effort to figure out which one's the best fit for us, for our project, for our needs. Maybe try out two, 3 different things. They may have overlapping features or behavior. We might need to use them in some sort of combination. So the problem is that there's no clear best tool for X. We kind of have to try them out, and sometimes they might be, I don't know, very powerful, but very difficult to learn, or have very poor documentation or usability issues. Otherwise, they might be very ergonomic, but lack the power features. And you kind of have to go through a discovery process to learn a bunch of them and figure out their strengths. Like if you figure out a particular tool might be useful for your project or for your needs, spend the extra effort to become a good user of that tool. Learn to use it, learn the power switches, learn the command lines, the hidden things, the power knobs to actually make use of that tool in depth. A good starter kit, if you're not aware of this resource, recommended. Jason has, I think it's a markdown in his repo of a list of, I would say, mainstream tools. It's not an exhaustive list, but the mainstream kind of things that you would need for a C++, for a generic C++ project. I put the link there, and from the screenshot you see there's a bunch of them around. If any of these sound unfamiliar to you, maybe spend a bit of time to just click through and see what's that all about. So I would say the problem with C++ is not that it's not easily toolable or that we lack maturity in the tools, is that we have too many to choose from and we have to spend the time to become efficient with them. Okay, moving on. Periodic reminder that you can interrupt me and voice your opinion at any point. Another myth is that C++ is slow to compile. And depending on what you're doing, it can be very painful indeed. But it's all about the structure and the build configuration you have. So from what I've seen, the majority of people think they know why their builds take too long. They say, it's a crappy compiler, or we have weird configuration or some particular needs in some way we want to build stuff. But you'd be surprised. As with optimization in general, build optimization has the same kind of surprises. So you actually need to use tooling and inspect to see what the culprits are. Sometimes it's not what you think. In your build bottlenecks, the causes might surprise you. So you need to use good tooling and investigation techniques to find out and figure out ways to improve. I'm going to elaborate more on that. There's multiple ways to improve your build throughput and to screw it up. So again, depending on what you're doing and what your project, how it's set up. So from build configuration to the project graph dependencies, the way you use compilation firewalls or Unity builds, or the way you use precompiled headers. If you're misusing header units, you can even the way you use build caching, you might think that you're improving your build, but you might be hurting your build in certain workflows. So you need to actually figure out what's going on and thoroughly measure to see an experiment to see what the underlying issues are. And people usually use various build accelerators and file system techniques and all sorts of shortcuts and tricks. But sometimes the prescribed or common wisdom accepted way of improving your build might, if you're rolling it out without actually checking what's going on, might actually be detrimental. Nice little tool if you're not familiar with it. I put the link there. It's a good way of gauging usage or impact of using certain standard headers and even some third-party libraries that you might be using in your project. Again, this is not to be taken as absolute. The absolute numbers are irrelevant. Just to give you a ballpark impact of certain things that you might be using and might be detrimental to the build. Again, don't take it as absolute things. Use it as a reference and maybe see, okay, maybe I'm using these headers, or maybe I'm over-including these. And more on tooling. So I said use tooling to investigate what's going on. How many of you are familiar with Clang F-time trace? See far fewer hands than needed. Okay. If you're using Clang, you should be familiar with this. And for other tool chains, I'm going to show similar things. So there's F-time trace is a very powerful tool. But sometimes I hear that it's not as ergonomic, not as friendly. It's a command line option, and it prints a very detailed report, and some people have difficulty understanding and learning how to use it. And there's a very nice, I would say, helper, Clang Build Analyzer, which has been upstreamed, so it's part of Clang as of version 9, I think. So Clang Build Analyzer, it's a much friendlier gateway into F-time trace. So it actually uses the same kind of thing underneath, but it's much easier to use. The reports are much friendlier, much easier to understand, to grasp, and start building an intuition for how time is spent during compilation in various stages of compilation, where time is wasted, or what kind of things are keeping the compiler busy. So if you're not familiar with it, there's good resources online, both blog posts and documentation. So get familiar with it, try it out, see what it tells you about your project. Even if you think you don't have a problem with this, it's good that you know how to use these kinds of tools when you're gonna need it. If you're on Windows, there's similar thing, VCPerf. Anyone familiar with VCPerf? It's an old thing. It's not new. So VCPerf is a way of instrumenting a build session. So it's sort of exterior. It's a kind of monitoring system. You start it up, you do your build, whatever setup configuration you have to build your stuff. Doesn't matter. The build is separate from the monitoring session, and then it just dumps a big trace file on disk, and this can be fairly big, like gigabytes big, depending on how long the build takes. And then later on, you can analyze this trace file using various tools. And one such standard tool on Windows is Windows Performance Analyzer, which is a generic tool to examine such ETL traces. In this particular scenario, the trace contains compiler-specific emitted diagnostics and timings, but the tool, the WPA analyzer, is generic, and you can find it in the store app. It's very easy to set it up and install it. The problem is that it's kind of a power user tool, so most people, when they use it and they open up a trace, they are so many tabs, so many columns. It's kind of overwhelming, and there's very precious information there, but it's definitely not user-friendly. So it has a steep learning curve. So you kind of have to know which tabs to look at, what columns are important, how to sort, what to filter out, and you will find the information there, but it's not user-friendly, at least not as a beginner using these kinds of things. And that's why we're building a better experience, better in terms of more approachable inside VS. So VS now has built-in support for build insights and can surface the same kind of information, but in a much more simplified way and much more actionable. It's integrated with the IDE, so it has all the expected code navigation facilities, and it has a much simplified user experience. Far fewer columns, only the thing that it would matter for you, at least at first stage of doing this analysis, and it gives you a better gateway to these kinds of investigations. So it gives you information about includes. You would see which kinds of includes are hot in your project, and if you're misusing the include graph, or if you're properly using PCH configuration and so on. You can even drill down into functions to see how functions are inlined. Some people, for performance reasons, like to abuse force inlining. You know who you are. And this kind of tool will show you when this extra time is spent and what kinds of consequences it has for the build throughput. So yeah, it will help. And for another way of approaching things, so things like VCPerf and Build Insights are tools that can do wholesale analysis, like they can do analysis on your whole project and do things kind of in batches. But you can also do these kinds of things as you're editing. So you can do things at design time when you're in the source code. Things like include cleanup. And how many are familiar with include cleanup like tools, like include what you see? Yeah, yeah, include what you use. Sorry. Okay, so we know the problems with these kinds of tools, and we have yet another tool. So no tool like this is ever perfect. But this is our attempt of providing such a workflow for design time, where you can see in the editor. I don't know if the projector is good enough, so you see that some of the includes are dimmed. That's configurable in the IDE, but by default, some includes are dimmed. So the ones that we notice that are not contributing to this particular source file are going to be dimmed, and you have in editor controls to remove and do this cleanup. And of course, no such tool, as I said, no such tool is perfect, and we're trying to build a great experience for this, but you do have to try it out and see how it works for you. If you care about these kinds of stuff, I do recommend this presentation by Vittorio. It covers a lot of ground, not just tooling, also techniques that you can use in code to improve build throughput. So there's various kinds of things that you can do. This is an hour and a half talk, so definitely I cannot cover this, but Vittorio did a great job, so I highly recommend watching this. So yeah, C++ can be slow to compile, but if you put some work on it, and if you're leveraging some good tooling, you can drastically improve it. Yep.
The recursion model, is that the major cause of the most slowness, or is it optimizing things?
Depends on the project. Depends on the project. Yeah, a lot of time can be spent in optimization stages and also in linking. But includes are a frequent way where we see that projects get stalled during compilation. Yeah, but of course, linker can be a big bottleneck and optimizations as well. Exactly. Exactly. Yeah. Yeah, I'm gonna tell that on record. So the comment was that linking is a big compilation bottleneck if you're doing link time code optimization, so or whole program optimization. So yeah, because that's where the majority of the time will be spent, and some parts of that pipeline are not parallelizable, but improvements have been made. And yes, the comment about building tests is relevant. Yeah, with tests you need to be even more careful, because with individual test drivers you don't care about whole thing optimization for test units. All right, moving on. The sad state of debug performance in C++. This is another common theme. We've been hearing this for many years now. I just want to pick one example of the zero cost abstraction is kind of a lie for debug builds. Again, it was a blog post by same Vittorio, just coincidence. He's not a troublemaker, I can assure you. I don't know if you read this blog post, but it's basically about the cost of using primitives like standard move and standard forward in debug builds. In release builds, this is a non-issue because all these kinds of functions are inlined away and it doesn't matter. But for debug builds, these end up being function calls where we actually mean for them to be some fancy casts, right? What we actually mean to tell the compiler is do that thing that's on the bottom right-hand corner. So why does it matter? Because people care about the performance of debug builds, and because they want to debug their stuff, and sometimes the performance on debug builds is so horrible that they cannot actually properly run their applications on debug. Probably most famous examples are games who cannot sustain acceptable frame rates on debug builds, and they do all sorts of tricks to tackle that. More on that later. So what we want is to have these functions behave as if they're just casts or intrinsics, even on debug builds. And up until not long ago, you're going to see not very old versions of GCC, Clang, and MSVC. So these are not very old versions. All these things, and by the way, this is O0, so no optimizations. All these things are actually function calls, and they do come with a cost. In more recent versions, and the versions are listed there, I'm not going to read them. In MSVC and Clang, now they are able to recognize these functions as special, and they will emit code accordingly, avoiding a function call. GCC, my understanding is that this is in the works, and it's going to come soon. So, in a word on implementation choice here. For example, in Clang, the decision was to treat these as special functions, as intrinsics, and do the compilation magic to avoid the function call. In MSVC, we took another approach of using implementation-specific attribute, MSVC intrinsic, for the purpose of having this mechanism be extendable. Because we heard users who have similar move and forwarding functions of their own, not the standard ones. You know who you are, game developers. And they want to leverage the same kind of compiler optimization. So they would want to decorate their own such functions with this attribute and leverage the same mechanism. If you want to learn more, there's a link to a short video presentation and a blog post about it. So this is just one part of the sad story of debug performance for C++. There's more stuff around this. So there's continuous effort in all tool vendors to provide. There's a question there, I'll take it. So there's a continuous effort from all tool vendors to provide a better experience, and there are various mechanisms in various compiler tool chains to achieve sort of a compromise between we want some optimizations so that the big debug builds don't suck as much, and at the same time be able to debug them. So we have a better way of debugging it, because we know that debugging release code is not easy. There was a question in the back. Yeah. Yeah. That's a tooling issue, and it has been solved in a bunch of debuggers that I'm aware of. So in the Visual Studio debugger, this is implemented as something called just my code, and a bunch of such standard library facilities are identified as not your code, and by default the debugger will not step into them. So it will pass through such adapter functions. And there's similar things in other debuggers as well. I don't know their commercial names. So it's not a unique thing. So it will work, and it's a tooling thing. So debuggers can work with many of these things, and we'll just pass through them. And not just these functions. There's many other functions that are considered not your code. There's a heuristic on what is detected as not being your code, and you can actually contribute that. So there's debugger profiles that you can edit yourself and tell it about more stuff that for the toolchain it looks like it's your code, but you consider it's library. I don't want to step into that. It's maybe, I don't know, game engine code. I don't want to step into that. I want to go through it and reach my code. So there's even extensibility points in debuggers where you can tell them what to do, and with this stepping behavior. All right, an interesting one, and we've heard today about this topic as well. So C++ will never be a safe language. And by safe, there's many things here like type safety, bound safety, lifetime safety, thread safety, many kinds of safety. And if you followed Robert's keynote this morning, you've probably seen a bunch of ideas there. Other talks that covered the subject, and I thought they were very good, at least I like them, are these. I particularly chose that screenshot with Sean pointing like that. And there's, I think all of them are now online. Maybe Timor's is not yet online, but all of them are probably online. So do look them up if you care about this subject. I would say that one of the things that we need to acknowledge with C++ is that undefined behavior. And even during the panel last night, if you've been there, this has been discussed. And in this morning's keynote. So until we have addressed UB and we have eliminated all UB in the language, we cannot really say C++ will be safe as a whole. So, and because we cannot eliminate all UB for reasons, and some of them have been thoroughly exposed, C++ will inherently never be a safe language, and we have to make our peace with that, because it's a trade-off. We kind of have to choose between performance and compatibility and portable and all sorts of desirable qualities for our C++ generated code and safe C++ code. So we're never gonna be there. We have to make our peace with it and strive to build better code. More on that in a minute. If you care about this and you want to read a proper treatise of this in written format, I recommend this article by Corentin Jabot. It's a fairly long article, but very, very good. It's about some of the dogma around safety in C++, some of the realities, some of the unavoidable yucky parts, and of course talks about UB and bounding and unbounding undefined behavior. In general, if we're maybe restricting this discussion to lifetime safety, because a lot of the discussion on memory safety is about lifetime safety, there's many approaches in general that various programming languages out there take to lifetime safety. Some languages and frameworks use garbage collection. We have dynamic memory analysis that we can use, things like address sanitizer. We can statically enforce rules on references, either accept a unique mutable reference or multiple immutable references. And depending on where you see these, in which programming languages, you might have them being enforced by the compiler and language, for example, Rust borrow checker, or by the way you define value semantics in the language, for example, like we have in formerly known val, now known as Hilo. I guess it's pronounced Hilo. Or just outright disallowing direct mutation, like pure functional programming languages do, and implement mutation through the type system using things like IO monads. And for programming languages like C++, this comes down to tooling again. We're in the category of static analysis here. Static lifetime analysis, there's a bunch of tools out there, from Clangtidy, MSVC built-in tooling, and lots of commercial static analyzers, each with its strengths and sets of built-in detection and heuristics, and of course false positives, because static analysis tools cannot be without false positives. And I would say when it comes to our current concerns for C++, I would say we have to have in mind a new AAA for C++, and that should be almost always analyzed. And there's various C++ security technologies that we can use depending on toolchain and platform. I have a talk here that I can recommend that I liked. I had a presentation during the pandemic about ASAN. If you're curious about how it works under the hood, how ASAN works, how trapping occurs, how such frameworks use shadow memory and poisoned regions to detect out-of-bounds accesses and so on. So if you're interested in mechanics, you can watch this presentation. A somewhat recent development for dynamic analysis is continuum error, because in many situations, so the usual behavior of tools like address sanitizer is to trap when they detect such accesses in poisoned shadow memory. And they would trap and just terminate the process with a report. And this is useful, but at the same time, it's not ergonomic, because if you're using these as part of your CI/CD pipeline and you're doing ASAN and maybe fuzzing somewhere in CI/CD, then just stopping such a process at the first problem, it's not practical, because you'll get a report, you say, it's obvious, okay, I'm going to fix this and do a PR and then run it again, and you're wasting a lot of time just back and forth, because probably that's not the only ASAN issue that's going to be detected. So continuum error is a mechanism to allow process execution and collect many such violations and have like a batch report with all of them, so that you can address them in bulk. So it's just a more efficient way of working with this. Link to another short talk about the topic. If we're talking about static analysis, there's like I mentioned, usually there's a lot of false positives, and the tools try very hard to have smart heuristics and algorithms to figure out what to alarm you about, but they can only do so much, because C++ is not an easy language to reason about, and in following references and pointers and doing escape analysis and lifetime tracking, it's very difficult sometimes. So there's mechanism where you can help static analyzers, again, using some custom attributes. Clang has had this for a while now, a lifetime bound attribute, and MSBC has a similar one. Again, if you're interested in the topic, like a 20-minute presentation and some resources there to navigate. So C++ will never be safe, and we will never have guarantees, but we can build a better program, build more confidence that what we have is safer, using good tooling, of course. And now we're getting to the interesting part. I don't think Rust was mentioned enough at this conference. So when the CTO of Azure posts a tweet like that, people usually listen. And I think they're sometimes overly enthusiastic about such efforts, but there's some truth behind it, and I'm going to show some real efforts towards Rust. They care a lot about things like Rust, not just because of memory vulnerability or memory safety. Some projects, that's a big concern, of course, but some projects do care about Rust also for efficiency. For example, lots of services out there who have tremendous scaling issues and tremendous costs of running those services just because of the scale. And those services are written in maybe managed languages. Some of them are written in C#, .NET, Java, Go, whatever. they're interested in things like Rust to save a lot of money. And this article is about secure cloud computing. It's a very long article. It's a good one. I would say the gist of it is that you build trust by using Rust. No kidding. That's the gist of it. And I'm going to show a bunch of ways Rust has crept in and how various teams or projects are actively looking at it. So Rust already is in the Windows 11 kernel. So there's a bunch of things that are implemented in Rust, and you can spot them easily. Rust is in the Linux kernel, 6.1. And even in Android. I'm going to have some information about that as well. So I can disclose some information because it's already publicly available. So there are a bunch of components from Windows who have been rewritten in Rust. There are two important examples, direct write and GDI. These are fairly core components of the operating system, and at least one of them is very old. I think it's older than me. So bringing Rust into Windows, of course, for stability concerns and avoiding memory vulnerabilities and exploits, it's a staged approach where you learn how to crawl before you learn how to run. So you kind of have to do exploration to see, okay, what are the costs of learning Rust? What are the costs of porting to Rust, of maintaining a mixed source code of C++ and Rust? What are the performance implications and so on? So it's not an easy process, but we're already on that path. So the first experiment that was done was with direct write, just because it's much better defined in terms of boundary component of the operating system. This component is responsible for all text layout rendering in Windows. But it's not a very old component. It's fairly recent. I think it was developed during the Vista timeframe. So it's a post-2000s component written in C++. And this was the first experiment that was rewritten in Rust. And it was a cautious and long process, but it was deemed a success. And because most things in Windows kind of have a COM surface, and you can interact with them through COM, this is one such case. And this component has projections both in native and as well as projections to be consumed through COM interfaces and to be used even in UWP and modern kinds of UI applications on Windows. COM actually provided a nice boundary for interrupt with C++, because all these components, even one like this one, which is fairly well carved out and sort of independent, has to interact at some point with other APIs, with other parts of the system. And the COM boundary was a good place to figure out how the interrupt story should happen. And you should be able to call C++ code from Rust code and vice versa. And there's been lots of experimentation here and figuring out good techniques. And it turns out it's not as hard as people thought. Usually people think that C++ Rust interrupt is very difficult. It has its challenges, and of course, those are the places where you will have unsafe blocks in Rust and so on, and less guarantees about things that will happen. And because it's a gradual process, when you begin, it kind of looks awful, and you kind of panic because you end up having lots of unsafe regions and unsafe bits when you interact, because it's a gradual rewrite process. But as you rewrite more and more stuff, you reduce the amount of interop that you need to do, because you end up having fewer such interop boundaries as you rewrite more and more stuff in Rust. So it's not as scary as it seems when you're embarking in such a project. The second experiment, and this one was a bit trickier because the GDI component, which is responsible for all 2D rendering in the operating system, this is a very old component, like 80s. I think it was developed during the 80s. And it's written in C++ and C. And of course, it has a much larger surface area. So this is a much riskier project. And efforts to rewrite this are more complex. But this experiment is also, okay, officially, I don't know if this is complete, but it's almost there. And a lot of changes have been made. It has been rewritten. Performance is on par with the previous implementation. There's unsafe bits around, of course. There has been a syscall made in completely safe code using Rust. So there have been syscalls in Rust around this component. And there's been even contributions back to the Rust project through the efforts of the team involved here. And there's more such oxidation efforts in progress that I'm not allowed to talk about. And that's not a unique Microsoft concern. So a lot of companies are seriously looking at this. There's a very nice case study that I recommend that you read. It's linked below. From Google, Google's Rust journey in 2022, and it's sort of formatted as a myths kind of thing, but they call it rumors. So rumor one, Rust takes more than 6 months to learn. They found that on average, the ramping up is I don't know if you can read it, but the red big pie portion is 1 to 2 months, and the yellow one is 3 to 4 months, and the blue one is 2 to 3 weeks. So the majority of developers can pick it up fairly quickly. Okay, they'll not be Rust experts, but they'll be proficient in it. Rust compiler is not as fast as people would like. Yes, sometimes it's slower than C++. All those checks come at a cost. People usually think that interop and unsafe blocks are the biggest challenges, and those turn out not to be the case. And of course, amazing compiler error messages and high quality of generated code, because Rust leverages the LLVM code gen backend. So the results are good. So again, a good case study article if you want to dig into this. Another article from the Chromium project on Rust and C++ interoperability and some of their desired goals around this interop. Turns out this project was not very favorable for Rust. The Chromium team ended up using their own thing. They're leaning more towards lifetime bound notations in C++, so that path that I mentioned earlier, and they have their own memory management system in their it's called OilPan. If you want to learn more about this, there's a bunch of resources out there. I linked one of them here. One mention of the unsafe block. You want to try to minimize the extent of these blocks, because in principle, unsafe blocks have more UB than C++, because in C++, compilers will work very hard to do alias analysis and escape analysis and figure out what's going on. with references and pointers to avoid weird things, whereas unsafe Rust blocks are just all bets are off. Okay. So moving on to, because we talked a lot about Rust, successor languages are going to eat our lunch. I heard this today over lunch. The one in the middle, high-low, is Val, previously known Val. They changed the name. There was like a conflict with some other thing named Val or something. And Carbon. So Val aims to be fast by default, safe by default, simple, interoperable with C++, strong whole part semantics, mutable value semantics. It's basically Swift without classes and reference semantics that came with classes. So if Swift had only structs, that would be close to what high-low aims to be. So it's a simpler, better Swift. The reason why Swift has all those things is because they share the object model with Objective-C, and they have to support everything in Foundation and UIKit and AppKit. Carbon similarly aims interoperability with C++, better defaults than C++, that's not hard. No function overloading, no exception handling, no multiple inheritance, no row pointers, no destructors, and so on. If you want to learn and see a nice overview of all these things, all these efforts, this is my favorite article by Lucian Teodorescu, The Year of C++ Successor Languages, published in ACCU Journal. Oh, and I forgot, Rust is perfect by construction. All right. Another case study with Android 13, I believe is still the current version of Android, current stable version. Memory vulnerabilities year over year. We see that memory security vulnerabilities are decreasing, and there's a reason for that. The reason is that the Rust chunk is increasing year over year, as well as Kotlin. And we can see here a breakdown between memory unsafe code and memory safety wins. So there's a correlation there that we can see year over year. And if we're looking at language distribution in the Android 13 source code, we see that C++ is more like stable, a bit decreasing in the code base, but Rust is definitely increasing version over version for Android. So there's a trend there. So I would say that it is plausible that they're gonna eat our lunch, but not necessarily. It's not necessarily a zero-sum game. There will be enough work for many years to come for all of us. But we need to know that such efforts are going on. We need to know where to cut our losses and where we can do a better job using alternatives. So takeaway would be to keep an open mind and not be fanatics. We're not language fanatics here, right? All right, moving on. Ranges, another myth. Ranges are safer than iterators, and all our experience with iterators since the 90s tells us that they should be. But ranges do come with some gotchas, and particularly views come with gotchas. And I call this my Nico slide. They're not particularly specific issues with views. They're issues with reference semantic things, and views have reference semantics. So all the usual gotchas around reference semantics in C++ apply to views. So, but they also apply to things like string view and span and all other things all other vocabulary types that have reference semantics, and they might trick us. So as always with C++, const is shallow and doesn't propagate as you might expect with references. Some of these functions do caching, functions like begin, empty, filter, drop, and so on. So you need to be careful about using them. Don't try to hold on to views or try to reuse them. They're not meant to be used. They're cheap to copy. Try to copy them or use them ad hoc as temporaries. Same advice I would give for a span or a string view. also applies to views here. Don't try to store them. Don't try to prolong their usage more than necessary. You just have to pass them around and use them. Don't hold on to them. So there's many gotchas, but people sometimes associate these kinds of gotchas with underlying issues with the concept of using ranges and range views. So ranges and range views are great, but if you fall in these kinds of traps, you will get the wrong impression that, oh, this kind of stuff is unusable. It's the risks overweigh the benefits, and it's not the case. So I mentioned Nico's presentation. This is the link to that presentation. If you want to watch it, he goes into a lot more details about these kinds of traps. This is my favorite example by far, and it's because you would be so tempted to do this, like use a range 4 through a monster collection where you filter out and you want to get all the dead monsters or the zombies or whatever. And then you would just want to resurrect the monsters. So this is undefined behavior, because a precondition for an invariant that needs to hold for filter is that its filter condition must not change while using this filter predicate. So if you're doing resurrect, you're violating an invariant that filter expects to hold for the whole duration of the iteration. So if you're doing this call and you're iterating, then it's undefined behavior. And it's so tempting to do things like this, because that would be one of the reasons why you care about filtering out a particular type of entity, so that you can change its state in some way. But if you're not careful and you're changing the very thing that the predicate, the filter, is all about, then it's undefined behavior. Again, a trap that you need to be aware of. Question there. Yeah, but people are used to that. Yeah. Exactly. The comment was that you can use the same kinds of mistakes with iterators, but people are, when they see code like this, it looks like innocent and fluent, and it sort of it looks like it's magical. It's supposed to work. So while with iterators, people are more careful because they've been burned. Okay. And closing up with CMake is the gold standard for C++ project system, and we've seen a few CMake talks already. And when it works, it's great. When it doesn't, you're regretting your life decisions. Patty said that. I don't know if she's here. I don't think so. The good news is there, again, tooling is meant to help here. So there's CMake debuggers now, and they're everywhere. So they're in Visual Studio, they're in VS Code. Just a short presentation here, and they're in a lot of editors. So they're in Rider and CLion. So there changes for these kinds of things have been upstreamed to Kitware. So they can be everywhere now. So I think this raised the bar for what you can do and the struggles you can have with CMake. So we must admit CMake is a challenge for many projects, and you can really mess up your build with CMake, or you might look at the CMake config and don't understand what's going on, because it went through so many iterations that it's unbelievable how complicated it ended up being. So having this be the norm now in many editors now, and potentially all editors from now on, because the debugger implementation that we did was upstreamed. I would think it will change the game. So CMake will be debuggable as normal code. It's okay. It's not the same kind of thing, but it will drastically improve the developer experience. And just as a sneak peek, oh, sorry, this. It's not very readable from the distance, but it's meant to give you a flavor that, and this is running in VS Code, by the way. So you can step through CMake, you can inspect properties, see their value, you can change their value, you can add things to the watch window and inspect stuff, you can change the values and run the script, continue running the script after you've changed the value. So it feels like a full-on debugger. It is a debugger. And I think it will help a lot to maybe understand a CMake config that you're seeing for the first time, or investigate some build issue, or even help you out starting writing one from scratch if you don't know what you're doing. And let's face it, most of us don't know what we're doing. So to close up, myth number 0, that was I had the same one last year. New C++ is the enemy of the old. I hear this a lot, and that before we had whatever shiny new thing in C++ 20, 23, whatever, I was able to program before we had that thing. Why do I need another complication? Why do I need a new feature, a new thing, a new way? Well, sometimes you don't have to jump for the shiny new thing, but many times is meant to simplify something, or build more confidence in the code that you write. So you don't have to adopt all the cool new things, but many of them are meant to help. So have an open mind, try them out, don't overuse them. Just because they're new, they're not supposed to be everywhere. And some of them are not maybe ready for prime time. We need a few years to build some experience around good usage patterns for them and figure out how they fit in existing projects. So it's a struggle. Fixing C++ is complicated because we cannot really move stuff easily. But we have to some sort of patch it. Other myth-busting series. This is one of my favorites by Patrice Roy, Some Programming Myths Revisited. Funny and engaging. And similar kind of thing in blog post format, 60 terrible tips for a C++ developer, is meant to be written in negative form, but it's about checks and problems that you can run into and gotchas. So they're terrible tips, but you can learn from them. So you can go through those. So I'm open for comments, contradictions, and provocation. Mm-hmm. Sorry, there was one? There was one tip, one terrible tip, double equals double. It's on the left-hand side down there. Yep. But there's an argument against that comparison of floating points is not so. So this addition that is inaccurate. And that's why you sometimes comparison I'll summarize the comment for the record. The number 14 there, double equals double. It's not an intrinsic problem of equality for floating point numbers. It's rather than about the operations that you did on the floating points, and then you're trying to see if their values are equal. So floating points are special kinds of members of our community. And there's, I recently saw, if you're a floating point skeptic or noob, I would say a very good resource I saw recently is Mike Acton. I don't know if people are familiar with Mike Acton of data-oriented design fame. He published a series of mini articles on getting starting with floating point and understanding floating point numbers. This is a very recent development. I think it's this month. So I can look it up and maybe add the link here to the slide deck. Very good series of articles on floating point, understanding how they work and some of the problems that you run into when dealing with floating point. Even things on fixed point that you need to know to understand floating point. So it's a very nice resource, and I would say it's very approachable. It's not full of very technical stuff. Other questions? Over here?
They go back to your example with ranges,
Mhm.
where you said that the invariant is broken
Mhm.
when you filter monsters and resurrect some of them. So, but can you elaborate a bit why do you think it's broken? Because like we have this sort of range, right? We
This
have a
is
mutable reference.
yeah.
So and then we already filter out some sort of a monster, right? We can do with them whatever we want, and then the filter goes further, and the previous part of collection
Let me-
is kind of not included.
Let me go to back to the so that people.
Perhaps I think wrong.
Yeah, this is the example. So again, there's a reason why I put this standard code here. This code will probably work if you run it, but violates what it says in the standard, so it may fail at any point. That's the whole point of undefined behavior. So filter, the way it is defined, it says that you are not allowed to violate its predicate. So if you're, for example, here, this one reverses the action of resurrect. So if at the end of this block, the observable behavior didn't change, you're not violating the invariant for that filter checks for. So if you're flipping it, say, okay, resurrect, and then the opposite, burn it, make it dead again. So if you're doing both operations, then it's okay, because the observable behavior for filter is that nothing changed. But if you're doing just one of them, then you are violating this condition. And it might work. I believe the implementations might actually work. But the way it's phrased, it's UB.
Filter, from what I know, might cache the first iterator, first boundary, and if you save it to a variable and then reuse a few times.
That's an implementation detail. So it might very well work. So if you try this, I don't think it will break. I think it will work as expected. Yeah. I haven't tried it, but I think it will work. But the way it's defined, it's UB. So that's not my job.
If monsters is like something like a set or a map, and it is somehow, and the key is somehow related to is dead, then this might actually break.
Oh yeah, if you're hashing by the thing that you're modifying, then for sure you have to do a two-stage thing where you're doing one pass to change stuff and then another pass to, or you will have to basically refresh the hasher if you're modifying the thing that you're hashing, like the key. Yeah, that's a classic thing way before ranges. Any other comments, questions? If not, I think they expect us for some kind of social event. So see you there.